Yeah, a mistake in the numbering of the questions on the tutorial sheet, and for whatever reason, it started started going again with another 5. So I didn't change the numbers. I just thought, okay, this is the second number 5. And we have to look at the exercises from the basic binary resource that's on the study desk. So here, binary is base 2. Binary is base 2. So the things that computers use. So again, we start with a ones house. We multiply by 2 this time to get the twos house. 2 multiplied by 2 is 4. 4 multiplied by 2 is 8. 8 multiplied by 2 is 16. 16 multiplied by 2 is 32. So here we have base 2 place values. How do you think we can work out the value of this number 101101? Any thoughts? These ones are worth different things in different positions, aren't they? All right, and this is one of the properties of place value, is that the same digit in different places has different bits together. That's right. We have to multiply multiply each value by its place value. So I've got this one here in the 32's house is worth 32, while over here this one in the 4's house is only worth 4. All right. So yes, we've got to add these all together. So what we need to add together, if I just clear the screen again, this one will be worth 32, the 0 will be worth 0, this one will be 1 by 8, which is 8, this 4 will be 1 by 4, which is 4, the 0 by 2 is 0, and the 1 is worth 1 in the ones house, 1 by 1. Okay, so when we add those up, or just before we do, what we've just done actually is applied the multiplicative property of place value. We've multiplied the house value by the digit value. And yes, we end up with 45, that's right. Okay, because we have to add these together. And this is a second property of place value, or another property of place value, where the value of the number is equal to the sum of the digits, the sum of the value of each of the digits. So we have to add these up. Now, why are we doing base 2? Why aren't we doing this with base 10? Well, I'll show you why doing it with base 10 is, how can I put it, so simplistic that we don't even think about it. If we've got 456 as a number, then, what's it worth? It's worth 456. Well, what are we trying to prove here? Okay? Whereas if we did the same exercise here, we'd have to think that this is 100. That's the 100th house. The 5's in the 10's house. The 6 is in the 1's house. And what we'd do is we'd say to ourselves, the 4 is actually worth 4 multiplied by 100. So it's worth 400. The 5 is worth 5 multiplied by 10, which is 50. 6 is worth 6 multiplied by 1, which is equal to 6. Okay? And then we'd add them all together and we get 456. So, which is what we started with. And people say, well, isn't that silly? It's not till you really start to look at a different base, like base 2 here, that you start to see what the numbers in the different positions really mean. Because when we look at 456, what's it worth? It's worth 456. Okay? And if we go through the process, you keep thinking, 400's worth 400, Whereas when we look at it from a base 2 point of view, the meaning of the place value really comes to light. Okay, what about this last one here, where we've got a 1 in the 32 house, a 1 in the 16, a 0 in the 8, a 1 in the 4, a 1 in the 2. What's it going to end up with? And a 0 in the 1. That's right. It ends up being 54. Okay. In question, it says, here's the first 6 place values. What will the next 6 be? Well, each time we have to do what? We have to double it. We have to multiply by 2 because it's base 2. Binary is base 2. So what's the next one going to be? 64. Then double 64 is 128, and so forth. Okay, so I've just put in the answers there for you. So double 32 is 64, double 64 is 128, double 128 is 256, and so forth. You might see some of those numbers and associate them with memory cards and for computers and things like that, because computers use base 2, and there's a relationship between the base 2 numbers and what we talk about with memory and computers. All right, here's a couple more conversions. We've got to work out what each house is worth. And what I normally do when I work these sorts of questions out is I write the house values just above each of the digits. So you always start with a ones house, then you multiply by 2 because it's base 2, and you keep doing that. And so what we end up with is 128 multiplied by 1 is equal to 128, and so on. Okay? And so you have all of these numbers that we then have to add together using the additive property. So we end up with 255. Now, the one at the bottom, just be careful with it. You've got a 1 in the ones house, and you have to work out what house this other one's in, don't you? Just notice that it hasn't got as many digits in it as the previous question. So what do you think the answer to part B will be? Yes, that's right, 65, because when you put the numbers above them, there's actually 64 in the ones house, is where this one is. It's in the 64's house, and this one's in the ones house. Question 4 and 5, I'm sorry. Okay, how can we tell, looking at this binary list on the side here, how can we tell if a binary number is odd or even? Yeah, 2 is not actually 1, 1. 2 is 1, 0, because the 2 is in the 1 is in the ones house. Sorry, the first one is in the 2's house. So 1, 0 is actually worth 2. Anything ending in a 0 is actually going to be an even number, and anything ending in a 1 will be an odd number. To work out what the next 6 binary numbers are, starting with 11, have a look at what's happened up here. We start with 1, and then when we go to 2, we have to move. If we add 1 onto 1, we end up with 2 in the ones house. But you can't have a 2 in base 2. You have to trade 2 1s for 1 2. And so you end up with 1 0. And then we can add another 1 to get 3. So you just add 1 and 0 is 1, and so on. Okay, so what's going to be 11? So you've got 1 1. So 1 0 1 0 is 10. And if we add 1 onto that to get 11, 0 add 1 is just going to be 1 0 1 1. And you can check it by thinking that this is a 1, add 2, which is 3, no 4s, and 8 is 11. Okay, what's going to happen when we add another 1 to get 12? That's right. Because we add 1 onto 1, we have to trade, and then we'll have to add 1 2 to 1 2 to get 2 2s, so you're going to have to trade again. Okay, so we end up with 1 1 0 0. What do you think 13 will be? That's right, 1 1 0 1. Now I know some of you will be sitting there thinking, what the heck's going on? Okay. my suggestion would be get a place value map with ones, fives, etc. Ones, twos, fours, etc. Base 2 place value map, and get some paddle pop sticks out and see what happens. And yes, that's right, there is a pattern. What about 14? What's going to happen with it? 14 is 1 1 1 0. Okay, because we have to just add the 1 and trade the next place. And then 15 will be 1 1 1 1. And what's going to happen when we get to 16? It's sort of like adding 1 onto 9,999, isn't it? Yes, we're going to have to go to the next place value. Now, those questions were pretty heavy going with base 2. The previous question was all on base 5. When you're trying to work out the value of the places, there's always a ones house. You start with write down the ones house, and then you can work out what the values are by multiplying by the base each time as you go to the left, no matter what the base is.